So what do you want to show? We want to show that we have some function f Rn to R twice differentiable, and we want to show that f is convex if and only if the Hessian is PSD for all x. That's the statement that one would want to prove. We know that we've already proved that if we have some function g from R to R, which is also twice differentiable, then this is convex if and only if the second derivative is greater than or equal to 0 for all t. Okay. The easy way to do this is to use this particular result. Okay. We know that f is convex if and only if g of t, call this g x comma y of t, which is defined as f of tx plus 1 minus ty, is a convex function of t for all x comma y. Right, we saw this when we defined convex functions. Essentially, you take any convex function in Rn, you take a slice of this, then that slice should also be convex. So it should be a convex function of R. Correct? So to prove this, you just use these two results. All you need to do is, so we can show that f is convex if and only if g is convex for every x comma y. So when is g convex? When the second derivative is greater than or equal to 0 for all t. Correct? So find the second derivative of gxy of t, derivative with respect to t. Okay. Again, I leave it as an exercise, but the second derivative will simply be equal to x minus y transpose the Hessian times x minus y. Okay, it's a simple exercise. You just use the chain rule, nothing else. So why does this imply this? When is the second derivative greater than or equal to 0 for all x, y, and t? So this has to be PSD for every point in its argument, right? Because if this is PSD, then certainly any vector transpose times this matrix times the vector itself should be greater than or equal to 0, and vice versa. So that's one way of showing that convexity, you have convexity if and only if the Hessian is PSD. So I leave it to you to fill in the details. Okay. So in this class, I'd like to use some of the techniques. So in the next few classes, we'll try to solve some convex optimization problems, or some optimization problems that we can hopefully frame as convex optimization problems. All right. So let's recall what we've seen so far. we've seen that suppose that we have an optimization problem of the following form. Minimize some f0 of x subject to correct. Yes, so we'll revisit that a little bit, but for now we'll assume that these conditions always hold. Okay, we'll come back to that at a later point, but those are still technical arguments. Effectively, what it says is that there should at least be one point status condition. If you look it up, we'll say that there should be at least one point in the relative interior of your constraint set, such that all the sort of constraints, that there is at least one constraint that is satisfied with strict inequality. But yeah, verifying status condition in many cases is not very easy. But in most problems of interest, this is satisfied. So typically, if you have a convex optimization problem, you don't have to worry too much. You just go ahead and solve the KKT conditions. It's only when the function is non-convex that you have to look into all of these. You have to be more careful. Because in any case, if the function is convex, if the optimization problem is convex, then KKT already gives you a sufficient condition, so you don't have to worry. Correct. Sufficient is in general, it's not necessarily, it's a necessary condition. Correct. Yes. So typically we will not solve non-convex optimization problem using the KKT condition. Typically we don't. You try to use some other kind of approaches to solve this. At least for the purpose of this course, almost all the problems that we'll solve will be convex. Okay, so let's try to recall the problem, the canonical problem that we're trying to solve. We want to minimize some function f0 of x subject to a bunch of inequality constraints fi of x less than or equal to 0, I equal to 1, 2, 3 up to some m. We have m inequality constraints and hj of x equal to 0 for j equal to 1, 2, 3 up to p. I have p many equality constraints. Okay. In order to solve this problem, we can use the KKT conditions if the problem is convex. So the optimization problem is convex if all of these functions fi are convex and the hj functions are all affine. Okay, then we call this a convex optimization problem, and for this KKT conditions turn out to be sufficient. Yeah.
So if hj of x equal to 0 is not affine.
Hj is a function, right?
Yes, sir.
Correct.
So if that is not affine,
yes,
then we do not call it a convex.
We don't call it a convex optimization problem.
Using KKT in that case makes sense.
You can always apply it blindly, right? But it may not give you a solution. Right? It's no longer a sufficient condition for optimality. Okay, but it will give you some candidate point. That's it.
Convex, like it's not affine, but it's convex.
Not necessarily, because we've seen, right? We've seen an example where you can take a hj which is convex, not non-affine convex function, but if you take hj of x equal to 0, then that will correspond to a non-convex set. Yeah, right. And in general, if hj is not affine, then the set of constraints need not be convex, even though hj is convex. And in order to solve this, we can use the KKT conditions. Which are the first set of conditions. Okay, maybe let me, even before that, we define the so-called Lagrangian L of x lambda nu, where lambda is a vector containing m components and nu is a vector containing p components. So you have one Lagrange multiplier, one lambda Lagrange multiplier for each inequality constraint and one nu component for each equality constraint. This is just f0 of x plus summation I equal to 1 to m lambda I fi of x plus summation j equal to 1 to p nu I hi of x. And the KKT conditions basically say the following: you need to have fi of each of these constraints need to be satisfied. So fi of x should be less than or equal to 0 for all I. Hj of x should be equal to 0 for all j. But in addition, we had this other condition, which was lambda I fi of x equal to 0 for all I. We also need to satisfy lambda greater than or equal to 0. It has to be a non-negative vector. And lastly, the gradient of the Lagrangian taken with respect to x should be equal to 0. That's equal to the same, right? So like gradient of this Lagrangian is equal to gradient of f0 of x plus summation I equal to 1 to m lambda I gradient of fi of x plus summation j equal to 1 to p nu I gradient of h, just by linearity of the derivative. All right. And we solved one problem using the KKT conditions. I mean, a couple of very small trivial problems, but one problem that we saw was the water filling problem. How do you allocate power across multiple channels so that you can maximize the throughput? Correct. We'll see something similar today, a different problem, also arising out of information theory, which is what is a maximum entropy distribution? So given any suppose you have a distribution on some finite set. So what is a distribution? That's basically a probability mass function, p1 up to some pk. Let's assume that k is the size of the alphabet. So you can think of a probability mass function on k symbols as just a vector where each of the components is greater than or equal to 0 and all of the entries sum to 1, right? So each p vector basically determines the distribution, and we are interested in knowing what is the randomness present in a given distribution. So are certain distributions more random than others? Okay, so you can think of this intuitively, right? What would be the least random distribution? The least random distribution. Right, so basically with probability 1 it's equal to say 1, and with probability 0 it's equal to any other symbol. So you know for sure if I sort of construct a random experiment, so that you can think of randomness in the following way: you know the distribution, and then you take a random experiment where you draw a sample according to this particular distribution. How well can you predict beforehand what symbol you are going to see? Right? That's one way of sort of loosely quantifying randomness, again at a very intuitive sense. Right? In this case, obviously, if you know for sure that once the same symbol is going to come out every time you run this random experiment, then there's really no randomness in the system. You can call that sort of least random distribution. But the randomness is higher if it is very, very difficult to predict what symbol is going to come out. And intuitively, you see that if all of the symbols are equally likely, then it's very difficult to predict what is going to come out of your random experiment. Suppose that they're not equally likely. If one symbol has a higher probability than others, then your best guess would be that symbol. For example, if the probabilities were 0.9, 0.05, 0.01, and so on, and you have to make a guess as to which symbol will come out if I draw a symbol according to this distribution, what would be your guess? The first symbol, right? Whichever has the probability 0.9, correct? But if all of the symbols are equally likely, 0.1, 0.1, 0.1, 0.1, 0.1, then really you can't do anything except randomly just all guesses are the same, right? So that's one notion of randomness of a particular system. Another way of quantifying randomness, and that's the strategy that is used in information theory, is suppose I am given a random symbol and my goal is to compress this. I have an alphabet of k symbols, and I observe an IID sequence drawn according to this particular distribution, and my goal is to compress this particular sequence. What is the minimum number of bits that I need to compress this sequence on average? It turns out that the minimum expected length is equal to the entropy of the probability mass function, which is defined as follows: summation I equal to 1 to k pi log 1 over pi. Okay, the total number of the minimum number of bits that you require to compress an IID sequence of length n turns out to be roughly n times the entropy. Okay, with the entropy defined as follows, and this is typically log to the base 2. And this also, the entropy function has some nice properties that also corresponds to our intuitive idea of randomness. For example, the uniform distribution will have the highest entropy, and many other properties. Okay, but all of that is not particularly important for our context. Our goal is to find out what distributions maximize entropy subject to constraints. Okay, suppose that you know that, let's say, that your distribution has an expectation equal to something, expectation equal to 0.5. Then among all those distributions having mean at most 0.5, which distribution has the highest entropy, the most randomness? And this is a problem that arises in many scenarios, in physics particularly, and also in information theory. Suppose that the p vector corresponds to some kind of a noise. Okay. You want to know what is the worst noise distribution. For example, if you have a communication channel where you're trying to transmit something, a noisy medium, and you know that the noise is additive. So whatever you transmit, you receive the transmitted vector plus a noise vector. Now in many cases you don't know what the distribution of the noise is, but you can make some measurements and try to find out, let's say, what is the mean of the noise, what is the variance of the noise. So given that the mean is equal to this and variance is equal to this, what is the worst noise distribution? And we'll take that to be the maximum entropy distribution. Okay, so that's some motivation, but the end goal is to always try to find out which distribution maximizes the entropy. Of course, here we're considering a discrete entropy problem. Okay, the distribution is over a finite set of symbols, but all of these ideas can also be applied to both for PMFs over an infinite alphabet, as well as probability density functions when you have continuous random variables. So how do we formulate the maximum entropy problem? The goal is to maximize summation I equal to 1 to k pi log 1 over pi, subject to, of course, the first constraint is that the p vector should be a PMF. So p greater than or equal to 0, summation over I pi should be equal to 1. But in addition, you may also have certain constraints on expectations. Okay, it could be the mean, it could be the variance, it could be a bunch of different quantities. And in general, all of these can be formulated in the following way. So summation j equal to 1 to k, some alpha ij, pj should be less than or equal to some beta I equal to 1, 2, 3 up to m.
Variance.
I'll come to that. Right? Okay, so maybe I should use a different symbol here. Let me call this alpha Lj Pj less than or equal to beta L for L equal to 1, 2, 3 up to m. So I have m different constraints that I need to satisfy. Okay, and let's see how mean, variance, and all of these constraints also are captured by this general formulation. For simplicity, I'll assume that the probability p, so pi, is basically the probability that x is equal to I. Okay, so basically x takes values maybe 0, 1, 2, 3 up to some k minus 1. But in general, it could be over any finite subset of. Okay, so what is the mean equal to in this case? For a given PMF, what is the mean equal to? It's equal to? Correct. So summation I equal to 1 to k, or whatever, I equal to 0 to k minus 1, pi times I. Right, that would be the mean. What would the variance be equal to? Or instead of formulating in terms of the mean and the variance, let me say the mean and the second moment. What is expectation of x square equal to? It's summation I equal to 0 to k minus 1 I square pi. In fact, I take any expectation, right, with respect to any function. It's always linear in p. Correct? In this case, the mean, it's a linear function of p. The second moment is also a linear function of p. Right? It's non-linear in this I, but it's linear in p. So no matter which I can take expectation with respect to any function. Let's say some psi of x. This is always going to be equal to summation I equal to 0 to k minus 1 psi of I pi. It's always linear in p. Yeah, psi is always a real value. Correct. So in general, I could just take these coefficients alpha Lj. In the case where I want the mean, it is alpha Lj equal to just j. If it's the variance, then alpha Lj is equal to j square, and so on. So any moment constraint can be very easily be posed as an inequality constraint of this particular form, right? Okay, so the problem, the entropy maximization problem, can be formulated in this particular form. So first, let's see. Instead of saying maximize, I could also say minimize summation I equal to 1 to k pi log pi. That just makes it easier. Okay, now what kind of a function is the entropy? Okay, and why is it concave? H of p equal to summation I equal to 0 to k minus 1 pi 1 by pi is concave. If you take f of x equal to minus x log x or x log 1 by x, this is a concave function. How do you verify that this is a concave function? Take the second derivative. What is the second derivative of f with respect to x equal to? Correct. So the first derivative is going to be, again, I'll assume that log is with respect to base e, just to avoid some unnecessary constants. So the first derivative will just be log x plus 1 or minus of log x plus 1. Second derivative will be equal to 0 plus or minus 1 by x square. Right. So this will be equal to 1 by x square, which is greater than or equal to 0. I'm sorry, yeah, this is going to be minus 1 by x square, which is always less than or equal to 0. So this is concave. Okay. Fine. So now I have this. So f of x is a concave function, or x log x is a convex function, and the sum of convex functions is always convex. We've seen that previously. You can express this as a sum of convex functions, and therefore this is also convex. All right. Now I said that the distribution that maximizes the entropy is the uniform distribution. And here's a nice way of proving this, right? And it uses just Jensen's inequality, which we've seen previously. So I have h of p, let me take summation, let me take h of p itself, is equal to summation I equal to 0 to k minus 1 pi log 1 over pi, right? But if you look at this particular expression, one way of interpreting this is that it is actually equal to expectation of log 1 over p of x. Okay. And what does Jensen's inequality do? So what kind of a function is log x? It's a concave function. So if I apply Jensen's inequality on a concave function, what should I get? What is expectation of log of something? It's less than or equal to log of expectation of whatever. In this case, it's 1 by px. But what is expectation 1 by px? Log of expectation of this is summation I equal to 0 to k minus 1 pi times 1 by pi. Both these cancel, and what remains is just k. So this is less than or equal to log k. So you may have already seen this in your information theory class, but it's a nice simple application of Jensen's inequality. F double dash of x. So this is minus x log x, correct? So this is equal to minus of 1 plus log x. Oh, sorry, it's not 1 minus 1 by x square, it should just be minus 1 by x. Right, so the second derivative will be, this is f dash of x, so f double dash of x will just be minus 1 by x. So f of x is a concave function. Correct. Correct.
Scroll a little down. Can you show how variance can also be written in the form of summation and
That's why I want to pose it as in terms of moment constraints. All right. So all the constraints that I'm going to pose are in terms of the moments of p. So the first moment should be less than or equal to something. The second moment should be less than or equal to something else, and so on. So typically, when you deal with this, you ensure that either you fix the mean equal to something, okay, or you fix the so for example, when you try to find the most noisy channel, consider the following scenario where you have a channel of the form y equal to x plus z, and you want to find out which z corresponds to the most noisy channel. Then you assume that the mean of z is equal to 0 or equal to something that you already know, and you try to maximize over all distributions having at most a certain variance or a certain noise power. But then in that case, the variance is just equal to the second moment. Because in any case, if the mean is fixed, then what is the variance equal to? It is this minus some constant. Right? It's expectation of x square minus expectation of x the whole square. Expectation of x is a fixed quantity, then that's already fixed. It's to maximize h of p subject to a bunch of constraints, because h of p is a concave function, or you minimize minus h of p. Correct. So you maximize summation pi log 1 by pi, or you minimize summation pi log pi. Okay. Any other questions? Okay, so let's try to solve maybe a simple version wherein we have only mean constraints. In general, we can try to solve this numerically. without using the KKT conditions. So perhaps let's do that first. Let's fix the alphabet size k equal to, say, 20. Okay. First, I need to define a variable. So p equal to of size k. And what do I need to do next? The objective, right? So I can say that the objective is, so what would be the objective? Correct. So it's to maximize something. How would I formulate this? Of course, I can say summation pi log 1 over pi. But in this case, there's already an entropy function, which is x log 1 by x. So I just need to say Cp dot sum of Cp dot entr of p. Okay. Now, what are the constraints? P is a vector, right? It's a vector here with k entries. Which, so Cp dot entr is just x log 1 by x. It's going to apply that to each component. Okay. Yeah, they could have called it something different, but what are the constraints? Yeah, correct. So p of course should be greater than or equal to 0. It's the first constraint. Summation of the pi should be equal to 1. Cp dot sum of p should be equal to 1. We can impose some kind of a mean constraint. So let me define what my actual alphabet is. Maybe I'll say that this is so let's say 0 up to k minus 1. So 0 k, but in principle I could have chosen something else, doesn't matter. For example, I could take this in steps of 0.1. Okay, so let's say I just have a mean constraint. So the mean of, so this is x into p, that's going to multiply this element twice, should be less than or equal to some quantity, let's say 2. Okay. So now how do I formulate the optimization problem? Problem objective constraints. So if I run this, then it will solve the problem. Okay, so just throw up a bunch of things. So it turns out that the maximum entropy is equal to 1.9 something. Right? So let's plot the PMF at which exactly that's what we want to solve. Fine, right? So let me call P opt to be P dot value x comma P opt. Okay, sure. I used stem this turns out to be the PMF that that achieves the maximum entropy subject to this mean constraint. Now you could also impose a variance constraint or a second moment constraint. So let's go ahead and do that. The only constraint that I need to add is that x square times p, which is less than or equal to, let's say, 3.
Second order moment constraint, or are you going to do x square minus p square? Or
I'm going to pose first and second moment constraints. Okay, in this case, the maximum entropy is lower. I've added a new constraint. It's 1.4, and let's plot this out. It looks something like this. Let me increase the mean and variance a little bit. Less than or equal to 6, 7. This is what it would look like. But if you've noticed, does this look a little bit familiar? Maybe let me plot instead of using the stem. It kind of looks like 1/2 of a Gaussian, right? And if I had only the mean constraint without a variance constraint, what does it look like? It looks like an exponential distribution. In fact, subject to a mean constraint, the entropy maximizing distribution is an exponential, and subject to only a second moment constraint and a fixed mean, it turns out that the entropy maximizing distribution is a Gaussian. Of course, I'm talking about continuous distributions. If it is discrete, again, there's no distribution that this corresponds to. But no matter what happens, we'll see that the entropy maximizing distribution always has an exponential form. Okay, it's always going to be e to the sum f of x. And that form of f of x depends on the kind of constraints that you have. If you have a mean constraint, then the f of x is going to be an affine function of x. If you have just a second moment constraint, then that's going to be a function, some quadratic. If you have a third moment constraint, it's going to be a cubic, and so on and so forth. It's going to be some quadratic.
Supposedly consider second moment will also guarantee that we kind of improving the constraint on variance.
Sort of, not exactly. Sure, it will correspond to some constraint, but the relationship is a little more.
Square plus square.
Correct.
So if we impose a constraint on x,
But true, in that sense, yes.
so depending on the constraint of variance, we transfer the constraint
To a constraint in terms of the second moment.
and optimizing these two problems in the same solution.
Yeah. Okay. Any questions? Okay. So yeah.
When we were talking about maximizing entropy,
Correct.
we told that it is maximum for the uniform distribution.
Yes.
So, if the uniform distribution mean is included in the constraint,
Yep.
then shouldn't the output be uniform distribution?
Let's see that. Right. So in this case, the mean. Let me choose a really high value for the mean. Okay. Let me say 20. Okay. The mean should be less than or equal to 20. You get the uniform distribution.
You were saying that the mean should match the mean of the interval group.
It's an inequality constraint, right? So in this case, the mean, the maximum mean that you're going to get is not going to be 20, but in fact just 10. So in this case, I mean, you're looking at all the distributions that have mean at most 20. Correct? And among those, what is the distribution that maximizes the entropy? 0 to 19, correct. Yes.
The range 0 to 90.
Correct.
With a mean less than equal to 20.
Correct.
The uniform.
Yes.
So that can uniform be expressed in terms of an exponential like that? Because it's still single parameter.
It's still a single parameter, but in that case, the exponent is just a constant. Which?
Exponential.
Okay, when I say it's a discrete distribution, right? So in this case, it's finite support. It has an exponential form, so it's e to the sum f of x. So appropriately normalized. We're talking about discrete distributions.
That x is 0. This kind of
F of x equal to 0 for all x.
But since the mean was within the range,
Correct.
then it would have been at some.
Yes.
So can that?
No, not necessarily. So even if I take, say, 12, right? I'm still going to end up with a uniform distribution. Because in this case, the unconstrained minimum is equal to the constrained minimum.
When you did previously, it wasn't this.
Correct, because I chose a really small value of the mean. So for the uniform distribution, what is the mean? It's going to be close to 10, right? 0 to 9.5. So if I choose anything less than 9.5, I will not get. I take 9, I'm going to get something that's.
The Gaussian, there were two parameters.
Correct.
You put two constraints, and
Yes.
there were two parameters. So it would be possible if you took the variance greater than, like if you put the variance constraint as greater than b minus a square by 12,
Yes.
or b minus a square by
Yeah.
8, whatever the variance is.
I get, again, I don't get a Gaussian in this case because it's A discrete and second it's over a finite alphabet. It's going to look something like a Gaussian.
But can it be uniform again if I change my?
Yeah, it will be. For sure.